Hello, everyone. Welcome to our final webinar in the JSRI Space Architecture series. My name is Sahba. I'm the founder of the Jordan Space Research Initiative. We are organizing this series as part of our ongoing space architecture design competition, where our participants are working towards designing our analog research facility, which we hope to build in the Jordanian desert in the coming years. So our goal is to work on bridging sustainable development with space exploration and really focus on the synergies where we can help life on Earth through our space research and development. And today is our final webinar. We're very excited to have Dr. Barbara Imhoff here, who is a distinguished space architect. I first met her at the International Space University when I was doing my master's there. And she really has a lot of amazing things to share. So really looking forward to her talk. Welcome, Dr. Imhoff, and I will hand it over to you.
Thanks so much, Saba, for the introduction. And yes, I work as a space architect as part of my company, Liquifer, Liquifer Systems Group and Liquifer Space Systems. So we are three partners, Waltraud Hoheneder, René Václavicek, and myself, and we are all architects coming with an architecture background. And we have an interdisciplinary team here on board in Vienna and Bremen, comprising of space systems engineers and scientists, and sort of the core expertise of architecture. We work for the European Space Agency, the European industry, and international institutions, and also conduct research and technology development projects as part of the European framework program. I have to say, I come from an art academy, so I'm sort of working really across disciplines. I work with artists, I work with engineers, and I'm also have a Master of Space Studies from the International Space University and a PhD from the Technical University in Vienna. So it is very broad. Today, I'd like to tell you a little bit about our work, but also about the extreme environment of space and simulations and simulators, and then how this all actually comes together in a continuum, which we call the Earth-Space Continuum. So I'm here in downtown Vienna, so you might sometimes hear some other noise as well. Okay. So I hope this animation works. Okay, so you probably, I'll just, stop, do a little bit of stop motion, since apparently there's, you can't see it as fluid. So this is a very typical module. You see it comprises of a rigid part and a deployable part. It's a very important element of future space exploration. It's a greenhouse, a deployable greenhouse, and it's a sort of further development from our Eden ISS greenhouse. And as architects, we always have to work with engineers, and the engineering sort of expertise is sort of the prime expertise, and we are trying to sort of create the environments to make it habitable for humans. But first of all, the engineers need to ensure that the machinery is all there, and the air management systems, and all other parts of the life support system. So here you see all these different systems, which also plants need. So this is for plants, but also at the same time for humans. The nutrition system is, of course, for the plants. It's an aeroponic system, so it works with a very limited amount of material. There's only sort of the roots are hanging in the air, and they get sprayed with this nutrition solution every 10 minutes, and within sort of 10 square meters, this is what you approximately see of growth area, 10 square meters, you can produce within 9 months 300 kilograms of fresh vegetable. And you also, of course, need some preparation and some other section. And these greenhouses, despite whatever you see in other representations, visual representations for Moon and Mars, they need to be protected against radiation. So probably you don't have these nice glass domes as you sometimes see on early visualizations. So now I'd like to go into a little bit more, when we talk about space architecture. So this is an example for it, this deployable, inflatable module. But what does it mean to work for space, and what do we have to deal with? First of all, we have very different destinations and distances. Outer space, we say, starts with a common line, 100 kilometers in this direction, which is not very far. Just imagine 100 kilometers from you, where would you be? Would you already be outside of the city sprawl? Would you already be in the desert? It's very close. It's, in less than an hour drive, or maybe an hour drive, you're already there. So in this direction, you're already in space. Low Earth orbit is up to 2,000 kilometers. And then the moon is already 400,000 kilometers away. So let's say you would take a train with 100 kilometers per hour, then you would take 24 weeks by train. This is longer than the Trans-Siberian Railway. And it's only 3 days in a rocket. So that's why we need rockets, because we talk about completely different distances. And then Mars, of course, is even further away. So it's 56 to 150 million kilometers away, and it's 64 years by train, if we would take a train. But even with a rocket, it's half a year in a spacecraft. So it's really, we're going very far away to very remote, very isolated places, and they have extreme environments. We have microgravity, or we have 1/3 of gravity, or 1/6 of gravity for the moon. It's very different to this 1G we are used to, and our body is sort of grown to. Now we have extreme temperatures, minus 156 to plus 121. We have, for example, the equatorial temperature on the surface in, let's say, 10 centimeters height on Mars is approximately as cold, or and it's the warmest place on Mars, but it's as cold as the coldest place on Earth, which is minus 80, minus 90 degrees Celsius, which we have measured in Antarctica, for example, at the Russian Vostok station. We have a vacuum, we have micrometeorites. They can really harm spacesuits, they can harm space modules, and so they can put humans at risk if they just puncture the pressure shell. And we have cosmic rays. They are also very dangerous and detrimental to human health. So what does that result in? It results in a lot of challenges for building and living. First, we have to transport everything. So there are large distances, and we have to think carefully, what to take with us. It's like going on a hike, and you only have a backpack to pack. What do you take with you, and what you leave back? We have delayed communication when we talk about Mars, and we also have dynamic launch loads. So actually, we can't, we still have to make it very robust, even if it's only for zero gravity. We have a shortage of space because there is this limitation in transport. So what do we do? What strategies do we employ? Architectural strategies. They can be deployable, transformable strategies, or building with in situ material, as you can see on the right-hand side, or also creating spaces that are highly multifunctional. We have a shortage of resources, so air, water, food must be brought. But if we are, going further and further to Moon and Mars, we need to recycle. We need to create these closed loop systems where every resource is being recycled, where everything we bring is not being wasted, but waste is a resource in itself. And also we have to look at in situ food production. But of course, because as humans traveling in to these environments, we need a habitat, a greenhouse, a laboratory, power supply, maintenance vehicles, on the as a general infrastructure. Then as programmatic elements, we need, of course, areas where we can work, where we can gather, but where we can also retreat and have some private spaces. We need connecting spaces, circulation spaces. We of course need some, on the technical side, life support systems, and we need furniture and windows. But how do we do windows? From the space station, and as you see here on the right-hand side, you can have this wonderful view towards Earth. But when you're on Moon and Mars, you need to protect yourself. So your direct views are limited. Indirect views are possible, or views through screens, where you have a sort of camera projecting onto the screen. This is all possible. And then a lot of spatial atmosphere, in planning, when you plan for architecture, is really about light, about color, about materials. And light is cheap because light is really, how can I say, is very lightweight, and you can do a lot of things with it. So it's an ideal architectural building material for interiors in space. So space architecture, because it's a very complex thing, is really a multidisciplinary, or uses a multidisciplinary approach to manage all these complexities of space projects. And it is really a matter of collaboration. There's no single architect doing all of it, just because of the complexity of the project. I think the next big endeavor is going to Mars. This is from our Lava Hive project, an in situ resource utilization, creating a Martian base from Martian dust in a lava casting process. But Mars is, as we know, very, very far away. And for this, we really need to be able to actually go to Mars and build something. We really need to assure ourselves of creating new technologies. So we have to develop new technologies. We need a lot of things still for Mars. We need 100% closed loop life support system. We need an efficient food production. We need a rocket which takes us there, and we need something safe against the radiation for the travel. But there are also other sort of dual use technologies from human Mars missions. So there are different challenges, and then there are sort of technologies we need, and then you'll see in a minute that we also can use these technologies for Earth. So radiation, if we can treat radiation, or if we find either architectural or pharmacological solutions, then we can travel to Mars. But we can also build on Mars very differently. We need to find systems for this, the scarcity of resources, air, water, but also of energy supplies. Mars it's not, we probably need some, atomic power stations there, or some other kind of energy resources. We can't use solar light for a whole base. There are a lot of other safety and health risks involved, and we need a lot of hardware which endures these harsh conditions I was talking about before. So there are different kinds of technologies. We need either pharmacological treatments or some mechanical material protection against radiation. We need these closed loop life support systems. We need also advanced energy sources, automation and robotics, because the Mars base needs to be constructed autonomously. It's not going to be built by humans. So it's all autonomous. And we need reliable maintenance systems. And all this also has Earth application uses. So, prevention of some illnesses, or novel construction technologies, advanced resource management, energy conserving, high efficiency products, automation technologies, and sort of reliable, low maintenance systems, very resilient systems. I'd like to also demonstrate this, some of the technologies which are important for Mars through projects we are currently working on and are having developed. This is for novel construction methods or using in situ resources. This is an example for the Moon. It's Project Regolite. And it is about solar sintering. So we want to sinter elements with three-dimensional interlocking capabilities. So you can build them like Lego bricks, basically one-on-one. And also we want to create and sinter flat ground stabilizing elements. That is to create paths that are dust protected. So because the lunar dust is very dangerous and abrasive. And you want to do that only with the sun and the sand. So we want to use the solar rays on the Moon. The Moon has no atmosphere, so there's an incredibly strong energy source, solar rays. We bundle it, and then we put it onto the sand. And in this way, layers of sand we can glue together into these building elements, and we need no binder, no other resources from Earth. And we want to do that because we want to build habitats, shelters, roads, and launch pads. Here you see such an example. We tested with lunar sand simulant. And that is probably also an experiment you could conduct in the desert, or you can try to build your habitat from desert sand. It does work. I tried it myself to use this technology. And then you get these kind of elements you see on the right-hand side, but you see that they're still, from a technological point of view, they just need to be improved to become real bricks. We did 3 different tests. This was a test in the laboratory environment. So with an automated XYZ table. Then we did a test with a larger test bed, and it was not artificial light, but natural sunlight, which was bundled through that Fresnel lens. And then we also tried it in a lunar environment, in a vacuum environment. And the idea was that we want to see if we could create habitats which follow this structure you can see here. You see that it's a very thick protection against radiation and micrometeorites. You can see that here. And there are two layers, printed layers, and then there's a layer of loose sand. So this is really just sort of to hold the sand together. And inside there is still vacuum, and we create pressure vessels that are already in a radiation protected area. And in here we also have pressure, and that is our habitable environment. All these different 3D printing campaigns gave us different insights in how to develop the sort of the bricks, the interlocking bricks, and it's a dodecahedron shape. It's kind of stems from a space filler geometry, and because it's 3D printing, every element can be tailored to its use. And so you see here these 3 layers, and so this is then the configuration we used, which is also modular and can be built into a larger base. Inside such a protected area, one can also imagine to put a she habitat. What is she? She is actually something you probably will need during your simulations in the desert. It's a self-deployable habitat for extreme environment, and it was built to serve different purposes. Firstly, for simulation, but then also to see how first outposts on Moon and Mars could look like. And so you see that she could be used on Mars, on the Moon, but also on Earth, as in extreme environment in the Antarctic, or during disaster relief. It was the size of a container, and could be transported by a truck. We also see that on the picture. And at the same time, it could be folded and put together so that 2 of them would fit into a launch configuration. Here you also see how it was transported. And this is the deployment process. So it has 2, it can double its size. It's basically 28 square meters from 14, from that kind of shipping container in the middle. It can be enlarged to 28 square meters. Comprises of 2 crew quarters, a galley in the middle, a workspace, and a space for maintenance and hygiene here. And because it could be highly compacted, all the furniture, you see that here the beds, for example, could be stowed and transformed into an optimal stowed configuration. It was also modular, so you could create a she village or some other connections as you would need it. Here we see the sort of how it folds and deploys. I hope it also shows in your transmission. You see how the galley, how the furniture sort of deploys and folds. These are the crew cabins. And each crew cabin has storage, has individual lights. And here the workspace also has acoustic panels. You can see them here, shelves, seats, but spotlights and general lights. This is the galley, the meeting space. And then when we walk further through, we can see that there's also that hygiene cabin and a little workshop in front of it. So everything, all the furniture is deployable, and also the sort of half of the wall can be deployed from the hygiene compartment, so that it can become a more open space. Because it's so tiny, it has rounded corners so that the space appears in its perception much bigger. and we used special interfaces, suit ports, to sort of as doors to the outside world, for example, to Mars. This was really to protect Mars from the inside habitat, and to also from the macro, so no microbes can sort of escape onto the Martian surface, because when we look for life on Mars, we don't want to find what we bring there. Here are some interior shots from the just ready habitat. Yeah, so this is she is a simulation habitat. This is built for that. And I just want to run you through the rationale. So why do we need space simulations? We need them because we can simulate and prepare space missions. We can sort of conduct also valid research in a human scale simulation research, and we all need this to create a better understanding of a space mission. As Liquifa, we have been involved in many simulations. For example, with two collaborative rover project in an indoor simulator in Stevenage in the UK, Mars simulator. Then you see Moonwalk, that is underwater, 1/6 gravity, a lunar simulation. Here you see a Martian simulation in Rio Tinto, and Antarctica with the Eden ISS greenhouse. And this is really, all these are very different simulation or analog places like Jordan Desert. And different things are being tested, scenarios, operations, and overall settings. This is here the see how we also operate. We go into these situations and locations. We are simulation astronauts, so that we can really get a good experience. These are my colleagues, Walter Trojneder, René Václaviček, here as a simulation astronaut. And we brought the She habitat into a Martian analog environment, into a Martian simulation as part of another project, Moonwalk. Moonwalk was about human-robot collaboration, exploring unknown terrain with a little helper rover. And so suddenly, when you remember these pristine pictures of She, you now can also see how the interior changes. In the workspace, we had an astrobiology laboratory. In the little workshop and maintenance area, we had the local mission control. The spacesuits were really used for operations, and every spacewalk would start from here. And then one would explore the unknown terrain, and one would compare astronaut rover to astronaut exploration. So the closest you can come to space on Earth is for sure Antarctica. And this is the Eden ISS greenhouse. It was a double standard container. This part was the service section, and this part was the actual exploration greenhouse, the growth area. Here you see the service section. And here you see the Paul Zabel, who was a gardener for 1 year in the greenhouse in Antarctica, overwintering, and how he harvests sort of everything in the greenhouse. There's also, it's quite a lot of things to do. It really keeps you busy. And I want to show you, let's see if I can hold it here. Yeah, just a little bit. You see, here you see that here are the roots of the plants. And so they get sprayed through here with a nutrition solution comprising of salt, water, potassium, and then this is grown in a very efficient way. So you don't need a lot of water and you don't need any soil. And you see that also in addition to what they harvest, they also have a lot of, they have sort of an excess plastic container where they have, you see that here now, where they have all the leaves which are not being used. So you could make cellulose or a cellulose printer from it. This is now what landed then day by day, month by month in the kitchen of the Neumeier 3 station, the German Neumeier station, which was next to it, next to the Eden ISS greenhouse. And because it was so successful in the first year, that was 2018, 17, 18, it's still in Antarctica and being operated by the Alfred Wegener Institute. The technology the Eden ISS greenhouse uses is part of vertical farming, and it's vertical farming. It finds slowly its way into food production, and also it's into cities. So we can see this in cities. These vertical farms are isolated from the outside environment. They're highly controlled environments, and they're also highly productive because you can fine tune the airflow, the light intensity, which is very important, and the nutrients. And they have 12 to 16-day growth cycles, and they're up to 390 times more productive than a farm. So you can see that space projects, they yield a lot of technology development for terrestrial applications, and there are a lot of different space reciprocities. We have been developing a project which is called the spaceship, the city as a spaceship, where we look at, okay, how does a modern, densely packed, technology-driven city look like? And can we use self-sustaining technologies from space or other thought approaches to implement it in cities to sort of get more resilient and sustainable cities. So we're looking at resilient to decentralized modularity. In large cities, normally you have also large sewage systems and so on, but you can imagine that each city can be composed of small closed loop ecosystems, like a building, you know, which is where already the water, you know, it's coming from the top, but, you know, where does it go? And so I think that is also important to consider. How can I clean it and bring it back? Maybe use it for a greenhouse in the building, or for laundry, or for any other purposes. And then if I want drinking water, I have to sort of refine it a little bit more. So we also can harness the power of technologies and look at efficiencies, how we can make efficiencies in the subsystems, how we can improve them, make them smarter, and also share excesses. Like there's too much, let's say, electricity being produced through photovoltaic panels. Where can I put it? So we can really get self-sufficient cities, and also we look at waste as a sort of resource. In this context, I'd like to introduce another project where we were partner. It was led by the University of Newcastle, called Living Architecture, and it was creating metabolic applications, apps for transforming our habitats from inert spaces to programmable sites. What did that mean? That meant that actually we can create sort of bioreactors which are part of our life support system. And so we had 3 parts: microbial fuel cell to produce electricity, photobioreactor to clean the air, but also to provide air to a synthetic microbial consortium that would harvest the phosphate, the waste basically, and reclaim it so we can use it again for as nutrition for greenhouses. So this was meant as a 3-in-1 bioreactor. We're making it compact and dense, and we created a whole system which could sort of produce electricity, air, and reclaim valuable resources. It looked a little bit like a life support system. And in this sort of generic architecture example for a sustainable city, we designed this building as a multifunctional building with these living architecture batteries, with these bioreactors being integrated into this high-rise system. It has sort of different apartments, but also workspaces, shared offices, and a rooftop greenhouse, and an indoor vertical farm. And the special focus is given to the kitchen and the bathroom areas where the urine is being polished for usage in dishwashers, washing machines, and toilet flushes. And liquid and solid waste is being collected separately. And urine and grey water are processed through the bioreactor batteries in the circulation areas. And then the regained phosphate is collected and used as agricultural fertilizer for the greenhouses. And when we think more in these kind of terms, then we can really create more sustainable cities on Earth and combat climate crisis, and hopefully also master our waste problem, so that in the end we how can I say, we are more like, we behave more like as we were just for a picnic on Earth, rather than being so harmful to our planet and to the ecology which we need to survive. And if we have mastered to build cities as spaceships, then finally we will also be able to build spaceships like cities. Thank you.
Thank you very much, Dr. Imhoff, for this presentation. I especially love the city as a spaceship project, and when you're talking about the dual use with the and what they can do for Earth, it really aligns with our goals at JSRI, and it's very interesting to see, how many parallels there are and how space can help us live more sustainably on Earth as well. So to our participants, if you have any questions, please put them in the Q&A box. In the meantime, I had a few questions because you mentioned early on the importance of having kind of a combined rigid and deployable architecture. And it seems like that could have additional considerations. So when you're coming at it from a design point of view, what are the things that you need to really design for when it comes to, for example, the interface between these different sections or the materials that you're using?
I think the advantage of having rigid parts with deployables is that you can accommodate complex hardware infrastructure such as the life support systems in these rigid parts, And then, you know, in the spaces where, you know, in the living spaces, you can make them deployable, and then you can also make them bigger. This is a sort of a paradigm we used with She. So let me, you know, then I pull up this here. Then, you know, here are all the life support systems, the kitchen and the water and everything. And then here are sort of the crew cabins, the workspace, and so that doesn't require too much piping and cabling and so on. And the same, to be honest, we did for the first project, or for the first, which I showed. Well, maybe it's here. So when I look at this again, here are all the machinery, all the systems, then they stretch into here, but the core is here and that is fixed. And so I can ensure that this can be built and, you know, and tested and so on. So it's a safe building, and then the other parts can deploy.
Great. So I think essentially it really depends on the applications of what you're doing inside that space. And I guess for having an expandable space, especially for the area that humans would be working and living in, obviously that makes it more sustainable in the long term, that you can build on it and some more modular design. And that brings me to another question about the ISRU construction of the habitat, because that is actually one of our goals with JSRI, because one of our research areas is ISRU and robotics, knowing that, you know, for space habitats, we will need to automate that. And as far as I know, there haven't been any habitats that have been completely built using this strategy here on Earth. And I know you mentioned that you've tried to do this as well with the using sand and in situ material. Curious to hear what you think are the big when it comes to the ISRU habitat construction. Is it really feasible to build an entire, you know, habitat or facility using this method, or is it more of a technology demonstrator at this stage?
I mean, when you look at the mud housing, the clay houses, you know, which exist everywhere, but they're very famous in Mali, for example, in Africa. Then, you know, this is ISRU technology. So the question is, how can we roboticize, technologize, automate these processes? Because this is what we will need ultimately. We will need processes that can be, you know, autonomously, you know, can be activated, and then buildings are being built autonomously. So in that sense, I think that the question is in technology development, to be honest, because we know the material quite well. But then we have to get to know it, you know, how it behaves during during this additive layer manufacturing, and then we need, but you know, there's a lot of experimentation now with 3D printing and sort of cement or concrete. So maybe it's also it's a material matter, because the material needs to be such that it doesn't, you know, that it sort of keeps a shape and then hardens quickly under the extreme environment. So I think that, to be honest, there's a lot of unknowns, but some things can be simulated in, you know, on terrestrial grounds, or can be tested, and needs to be developed here anyway.
Yeah, definitely. And I find it interesting. You mentioned also the clay housing. And I think when we talk about ISRU research in space, we do tend to forget that this is how, you know, actually the humans on Earth have been using the resources around them. And a huge point of our inspiration as well, if you look at in Jordan, we have Petra and these structures, really grand cities that were carved into the existing the resources, the landscape. And so how can we get inspired by what we've already been doing here on Earth, and as you said, really develop the technology to do it in space, and automate that to some extent. And then I was also very interested when you were talking about the different simulations that you've been involved in. One of them was in underwater simulations. And of course, that gives a whole different kind of perspective of the things that you can study. I'm really curious to hear more about that project, and that is something that we're considering in the long term, after establishing a facility in the desert for the technological testing. How can we also do underwater simulations to complement that? So I'm curious to hear what the main differences were, what specific challenges you faced there. Oh, you're muted.
Thanks. So what can be simulated underwater? And first of all, it's a level of gravity or absence of gravity for space missions to the International Space Station. All the EVAs, the extravehicular activities, they are being simulated in water. And what we did here was also external. It was not inside the habitat, but external, sort of how one can move. But what you can also see on the picture is that actually the isolation factor increases. If you compare, let's say, that astronaut here on that picture with that astronaut, then you can already see that it's more eerie, more isolated, more, the danger increases. So while this is sort of, okay, yes, suit is heavy, it's hot and so on, and I need to fulfill my task. This is really, you can't just, I mean, out of these suits, you can't get quickly anyway, but underwater sort of that is more, it's closer to space than this simulation in that sense. It really depends on what you want to simulate. And then, of course, you could have an underwater habitat like She, underwater, and just, have people there for, like they have the NASA Nemo missions with the Aquarius underwater habitat. And you can isolate people, you can have them live in an extreme environment and see how they get along, but also outside then underwater, what kind of procedures they can test, maybe emergency procedures. Somebody is on an EVA, hurt him or herself, how can this person be rescued, etc.
Yeah, definitely in terms of the safety. I mean, our other analogs, in the desert or wherever it is on Earth, on the land surface, I guess, worst case scenario, people could always leave. And when it's underwater, safety is a huge concern. So it needs a lot of planning ahead, which is very similar to space in that sense. So I guess to wrap up, knowing that, you work on space architecture and also some space simulations or analogs, and knowing that our goal is to build this analog facility, that's what our participants are working towards right now. I was wondering if you had any advice for them on how to apply, traditional architectural ideas or space architecture more broadly when you're looking at simulations. Like, what is the process that you would recommend that they follow? Any tips or things that you've learned along the way?
I think it's really about imagining, what people would need and do in this. A simulation is always a simulation of a real situation. So what is the real situation, and what is meaningful to simulate, so that there is a reason. Okay, I need to simulate, let's say, exit and incoming, outgoing procedure of a spacesuit, because that's a critical operation. So, or I need to, see, or I want to find out, let's say, if a rover and an astronaut are, if it's more meaningful to cooperate or in which situation is it more meaningful than just astronaut? Or, what can such a small rover do for me? So this could also be a research question. So I think it's really about what could the research entail. And then, of course, one, living in such a habitat is a different kind of thing. It's all about, it starts with a selection of people, but it's always, creating this kind of, what do I want to simulate? Why do I want to simulate? What do I want to get out of it? And I think these things are extremely important to come up with a meaningful facility. If it's modular or if it's for a very dedicated simulation mission, doesn't matter. But I think that needs to be very clear, because then it can become a very good facility.
Yep, definitely. And I think also bearing in mind that we want to work on things that contribute towards sustainable development and, living in a more sustainable way, whether it's in a space habitat or on Earth. If that's your main driving consideration, I think it really guides kind of the way that your research is going. And with that, maybe Dr. Imhoff, you can share if anyone wants to follow up on the projects that you shared or anything, you can send us the resources and we'll be happy to email them to the participants.
I think I'd like to just say that we have an extensive website with all our projects, liquifer.com. And we also have a YouTube channel with a lot of documentaries and animations, lots of videos. So that's also a good resource.
Okay, amazing. So we'll check those out and we'll share them with our participants. So thank you very much again, Dr. Imhoff, for joining us and for wrapping up our space architecture series. It really ended on a great note. A lot of the things that you shared really align with our goals, and we're very happy to have you as a speaker. And for everyone who joined or watched on YouTube, thanks for joining. Stay tuned. We will be sharing more updates from our space architecture competition soon. We're very excited to see what our participants come up with, and we hope to host more series like this in the future. And thanks again to the Moon Village Association for supporting us as well.
Thank you very much.
Thank you. Bye, everyone.
Bye.